Okay, so let's talk about simple harmonic motion or oscillating motion. So here's sort of what we're going to go over. We have the motion of an object attached to a spring. We have this analysis model, which is a particle in simple harmonic motion. We're going to talk about the energy of simple harmonic oscillators, and then we'll talk about some other things like the pendulum, which is just a different simple harmonic oscillator than the spring. We'll talk about damped and forced oscillations, and that'll lead us to the cool topic of resonance. So let's talk about motion of an object attached to a spring. And we'll start out with horizontal motion. And let's start by defining oscillating motion. So oscillating motion is any kind of back and forth motion. So you displace something from an equilibrium and then it tries to go back, misses, goes a little bit the other way, and you end up with this cycle. Okay? And because it's a cycle, we need to know the period, because that's the time it takes to complete a cycle. And the frequency, that's just 1 over the period. And we also need to know just sort of this math that we've had for a while, okay? So here's our different sort of periodic functions. You can see the most common one is obviously going to be this one where you go up and down. It's a nice sinusoidal curve, but you can get anything that just repeats itself. That's any oscillation, okay? So just to sort of demonstrate what this looks like, you can see this thing, whoops, oh no. This thing is going back and forth. So you can see the block is moving back and forth between 4 and 8. Let's say these are centimeters, but it doesn't really have units, okay? Which means if you look at the block moving back and forth, oh, geez, back and forth down here, you can also see the block as it moves up and down on the graph. So you have the block moving back and forth, you also have it moving up and down, and you can see the highest point it reaches is 8, the lowest point it reaches is 4, okay? And so the maximum would be 8, the minimum would be 4, but the amplitude is the difference from the equilibrium. And where's the equilibrium? Where's the middle of this graph? It's going to be at 6. So your amplitude here is 2, okay? You're not oscillating back and forth between 2 and -2. You're moving back and forth a distance of 2 and -2 from 6, so between 4 and 8. So your amplitude, which we'll call A later in the equation, that's going to be 2, okay? You'll also notice that this thing is periodic. And what's the period of this? Well, if you look at where you get back to where you started, the period's at about 7, okay? Because you start at 0, you start at 8. Once you get back to 8, it's been about 7 seconds, assuming these units are seconds, all right? So we want to analyze this. If you took some sort of screenshots of this, here you could see this thing is oscillating back and forth between A and -A. So A, -A. So it's going back and forth, and this one's centered at 0. So you can see here, this is our equilibrium, this is our maximum amplitude, this is our minimum amplitude, and so our maximum amplitude we'll call positive A, our minimum amplitude we'll call negative A, and the period here is the distance from peak to peak, or from any identical point to another identical point. So from here to here could be 1.6 seconds, that's a period. From here to here is 1.6 seconds, that's a period. Okay, so anytime you get back to the same point you were at the beginning, that's what you consider to be the period. Okay? And you can sort of see how this plot would look if you were just plotting it directly over here. This is a lot like what the graph said. So simple harmonic motion, our position versus time graph is sinusoidal. And our amplitude is going to be considered our largest displacement. Okay? So if we look at the graph below, this is a position graph, so position versus time. Remember, if you take the derivative of a position versus time graph, what do you get? Well, you're going to get velocity, all right? So if we want to look at this, we want to know stuff about energy. So let's start by looking at what we're doing here. The graph below shows this displacement graph. It's a spring as a function of time. We want to know, where does the mass change direction? Okay, so where does the mass change direction? Well, basically it's going to change direction at C, right? It's going down, then it's going up, E, G, and I, okay? What's where is the sign for velocity, positive or minus? Well, then we're just looking at the slope, because when we take the derivative, the slope's going to give us the velocity. So if you're going down, this is negative velocity, right? These are both negative velocity. If you're going up, that's positive velocity. So the sign is going to be positive when your slope is going up and negative when your slope is going down. We want to know where the velocity is going to be 0. Well, that's anywhere where the slope is 0. So the slope is going to be 0, right? Wherever you have these flat things. So once again, C, E, G, and I, and that should make sense because we know that's where we change direction, and velocity has to be 0 if we change direction, okay? Where's the velocity maximum? Well, that's, the velocity is a maximum anywhere where you have a steep slope. So here, 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 and here, okay? And I guess that's speed because you have positive and negatives. And then where's the potential energy a maximum? Well, the potential energy is a maximum wherever you don't have any kinetic energy. So that's going to be, let's say we know the potential energy is maximum where we don't have speed. Well, look, we're stopped here, 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 and here, so that's where your potential energy is a maximum. Your kinetic energy is a maximum wherever your velocity is a maximum, so that's here, 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 and here. Okay? All right, so just to review, here's our exciting results. All right, so simple harmonic motion, we're going to get something that looks like this. Now, where does this come from? Well, we know that force, I don't really like that one. Okay, let's try a different color. Force is equal to mass times acceleration. But when we're talking about a spring, what's our spring force? Well, our spring force is going to be negative kx. And we also know that mass stays the same, that's a constant, but acceleration is d squared x over dt squared. So this thing becomes a differential equation, and we're going to rearrange it so we get d squared x over dt squared is equal to negative k over mx. All right? This differential equation, it turns out, has a general solution that's something like a cosine omega t plus b sine omega t, but that's sort of the general solution. It turns out the explicit solution is this, okay? So when you solve this, you get this. And the most interesting part is here we find that this omega is actually this. So omega ends up being a function of k and m. Now k is a spring constant and m is the mass. So this says your frequency is determined by just the kind of spring you use and how much mass you put on it. Okay? So this is our position equation for simple harmonic motion. It's always going to be this sinusoidal graph. This is your amplitude. Here you have your frequency. This is just time. And this is something called phase, which we'll talk about in a minute. Oh, here. Yeah, there it is. Okay? So this works for all simple harmonic motion, not just springs, okay? So when we pull all this stuff back, we can actually do this for pendulums, or if you just have a ball floating around in the bottom of a bowl. All of that stuff works with this equation, which is a little bit nutty, okay? All right, so let's talk a little bit about the math. Amplitude just tells us, you know, what our maximum and our minimum are. So those are our amplitudes. This is our position, so you can see this anywhere you are on this axis tells you position. This is our time, okay, that goes with this. And here's our period. Now our period is going to be related to our frequency, like we said before, okay? And here's the relationship. We have 2 pi over omega is equal to period. Okay, so that's how that works. Now let's just think about what that means. So omega is going to determine the frequency, okay? It's the angular frequency, so how many radians are completed per second. So if you make omega larger, then you make this graph sort of squished, and if you make omega smaller, it gets a little more stretched out. So you can kind of plot this onto a circle. You can kind of imagine that as you go around the circle, this is cyclical as well, okay? And there's a relationship here for a traveling wave. This brings us to this graph. So if we want to figure out this a function as of this mass oscillating on a spring, we want to know the period, frequency, an angular frequency of the oscillation, and we want to write an equation describing this motion, okay? So what's the period going to be? Well, you just look for 2 points where you come to the same place, okay? So the period here is going to be about 12 seconds. You just read that off the graph. All right, so if our period is equal to 12 seconds, that means our frequency is equal to 1 over 12 seconds, okay, so 1 over 12 hertz, and that means omega is going to be equal to 2 pi times the frequency, which is 1 over 12 seconds, so end up with 2 pi over 12 seconds, and that's going to be 2 times pi divided by 12. It's like pi over 6, so we make that a decimal. It's like 0.52. So we get something, let's just call it pi over 6, and that's going to be in radians per second. Okay, so that's the period frequency and angular frequency. If we want to write the equation, that's going to be x of t. Our maximum amplitude is 20, so that's 20 centimeters. We can change that to meters if we want. Cosine pi over 6t. And then our phase here, you can see this is cosine. It starts at the maximum, so the phase is going to be 0. And that's our equation. Okay? Oh. And yeah, we did that later. So look, if you want to think about the phase, that's a little bit trickier. So the phase constant describes your initial starting position. If you have a graph that looks like this is clearly cosine. It starts at the maximum. Okay? If you shift the graph forward or back, then you get a positive or negative phase. Now it's a little bit confusing because if you shift it back, you get a positive phase, and if you shift it forward, you get a negative phase. There's a sort of reasoning behind that. But the basics look like this. So if you have some phase constant, okay, let's say you have a phase of pi over 6. That means you've shifted this back. It's a positive phase, so the whole graph shifts back pi over 6. The way you want to sort of think about that is now it crosses the x-axis at a cosine pi over 6. So that means 70% of your original amplitude, or sorry, 86% of your original amplitude. At pi over 4, it goes down a little bit more. At pi over 3, it goes down a little bit more. And then at pi over 2, you'll notice your phase has changed so that this graph is no longer considered cosine. It's now sine, okay? And that's something we should maybe know. So if we want to do the sinusoidal equation for this, right, this one actually has a phase, but the first thing we want to do is we can say, okay, we know from how the period works that from here to here, that's about where we are on the period. So the period should be equal to 2 seconds. All right, that's about this far. But you'll notice, right, you'll notice that if you have the period, you can still once again get angular frequency. So that's 2 pi over t. So now you have an angular frequency of pi. Okay, that part's easy. We have an amplitude of about 10 centimeters. So when we say x of t, we have 10 centimeters cosine of pi t, but we know we have a phase because we don't start at the maximum. Okay, so anytime we don't start at the maximum, we have a phase. And the way we're going to figure out the phase is actually pretty straightforward. In order to find the phase, we just plug in an x and t, because look, we have x here and t here, but we have this whole graph of x and t, so we can just pick a point. And the easiest point to pick is going to be this one. So x at this point, x equals 0, and t is equal to 5. Okay, so you say 0 is equal to 10 centimeters. Oh, sorry, not 0. What's x? Did that wrong. X, right? X is not equal to 0. X is equal to 5 centimeters, right? This is x on this axis. And t is equal to 0 seconds. So x is going to be 5 centimeters, all right? It's equal to 10 centimeters cosine 0, because t is equal to 0, plus phi. So you can call, you look, this becomes 1/2 cosine, oops, 1/2 is equal to cosine of phi, which means phi is equal to cosine inverse of 1/2. Well, cosine inverse of 1/2, that's going to give you something that we should recognize, okay? And I'll give you a second to plug that into your calculator. Cosine 1/2 is something that's easy to calculate, and if you don't remember it, you always have the calculator. So, let's see, election. All right, so, anybody get it? Cosine 1/2, that should give you plus or minus pi over 3. All right, so we want to figure this out. That means we can see that this thing shifted back, so we're going to pick the positive one. And so we can write our equation as x of t is equal to 10 cosine pi t plus pi over 3. And this is our equation here. Oh boy, that's ugly. All right, so last thing, this is an offset. We looked at this in that little animation of the graph being formed by the spring that's moving. Offset just means you can just add an actual number and shift your graph up and down. Okay, so if you know this is your position equation, how do you get your velocity equation? You just take a derivative with respect to time. All right, and here's another example of setting up how to figure out what the position and velocity is. This is just plugging stuff in. Okay, so I want you to think about this. An object moves with simple harmonic motion. If you double both the amplitude and period, what's the object's maximum speed going to be? What's going to happen to it? So go back and look at this. All right, and you can see the speed is going to depend on A and now omega. So what happens if you double the period and the amplitude? Well, that means it's going to remain unchanged because the period doubling halves the frequency and doubling the amplitude doubles the amplitude. And since your V max, V max is going to be A omega. If this is times 2 and this is times 1/2, that cancels each other out. Okay, so that's going to make it unchanged. All right, here you can think about phase. We have these 4 different situations, and what does that mean in terms of which one has a phase constant of pi over 4? Okay, so I'll give you a second for that one. Pause. Okay, so think about a circle. Think about going around the unit circle. At 45 degrees, that means your particle, or in this case your mass, is in the first quadrant. It's going to be moving to the left, meaning a negative v, and if you plug in t equals 0, you get positive pi over 4. So that's going to look like this, okay? It's going to be moving to the left, but it's going to be over in the positive side. That's the first quadrant. All right, so dynamics of simple harmonic motion. Well, look, if the first derivative of your position equation gives you velocity, then the second derivative of your position equation gives you acceleration. Okay? And of course, this is what we call a restoring force. This is how we get the simple harmonic motion in the first place, because every time you stretch the spring out, it tries to go back. Every time you compress the string, it tries to go back to where it started. So it's always trying to get back to the equilibrium, and that's what you end up with. Here we have another long equation. I'll give you some time to think about this one, okay? just pause and you can look through what we did here. All right, so vertical oscillations are a little bit different. Once you hang something on the spring, you change its equilibrium length. And how do you know what its equilibrium length is? Well, remember, we know that equilibrium just means that forces have to be equal. So that means your spring force that's pulling up has to be equal to your force of gravity. That's your new equilibrium. Okay, so same behavior as if the mass is oscillating horizontally, you just have to find the new equilibrium length first. And we also just make this in the y direction, right? Because we know that this thing is moving up and down like this instead of like this. So this would be x, this would be y. So we say we have this student hanging from a bungee cord with a spring, and the spring has a spring constant 270 newtons per meter. If you pull the student down to a point where the cord is 5 meters longer than its unstretched length, then released, we want to know where is the student and what is his velocity 2 seconds later. Okay, so to find how far the cord is stretched, we need to set the forces to be equal, and when the forces are set to be equal, we know that, hang on, well, we know that mg, whoops, is going to be equal to KL. All right, so hang on, I gotta get this going. So here, our force mg, that's the force due to gravity, is going to be equal to K delta L. All right, we know what K is, and we're going to have to figure out delta L. So delta L, let's see, that's going to be mg divided by K. The mass is 83 kilograms. G is 9.8 meters per second squared, and this is going to be 270 newtons per meter. All right, so you plug all that stuff in and you get about 3 meters. Okay, so that means your delta L is going to be 3 meters. All right, we can also figure out our frequency, and since this, well, since the delta L is 3 meters and this is 5 meters longer than the unstretched length, how are we going to find amplitude? Well, amplitude is going to be equal to 5 meters minus 3 meters, so that means we're going to have 2 meter amplitude. All right, whoops. And that means when we make our equation, y of t, our amplitude is going to be 2 meters, and then we have cosine, and now we need omega. Well, how are we going to find omega? Well, we know omega is equal to k over m. We know k and m, so k is going to be 270, m is going to be 83. This is newtons per meter. This is kilograms. Oops, why is that? All right, so this is going to give us 1.8 radians per second, so this is 1.8 here, t plus the phase. It turns out since we are stretched down instead of up, so at our negative instead of positive amplitude, we can remember that if you go halfway through a full cycle, so a full cycle is 2 pi, that means we're halfway through the cycle. We've gone to our negative amplitude, okay? So that is our whole equation. If you want to figure out where you are 2 seconds later, you just plug in 2. So this is 2 meters cosine 1.8 times 2 meters plus pi, and this should give you 1.79 meters. So he starts sort of down here, and then he ends up here. Our equilibrium point's somewhere there. Okay? If you want the velocity, you just take the derivative of this, so that becomes negative omega a sine omega t plus phi. Okay? You plug in all these things here and you get negative 1.8 times 2 sine of 1.8 times 2 plus pi, and that should give you negative 1.6 meters per second. So here's your two values. So that brings us to our answer. If we want to deal with energy, right, we just have to figure out potential energies. Now, one thing to remember is the frequency only depends on your K and your M. So period and frequency do not depend on amplitude, all right? So if you have a block on a spring, you're just going through and adding up potential and kinetic energy again. All right, so if you have a block on a spring, it's pulled a distance of 20 centimeters and released. The subsequent oscillation are measured to have a period of 0.8 seconds. That's how we're going to figure out what our omega is. We want to know what position or positions is the block speed 1 meter per second. Okay, so we're just using energy the way we always have. But first we're going to figure out the period, right? Oops. Oh boy. Period of 8 seconds. That, or 0.8 seconds, that's going to be equal to 2 pi square root of m over k. All right. Once you do the algebra on that, that means k is going to be equal to 30.8 newtons per meter, and this is all you're going to need to figure out what your energy is. So remember, potential energy of a spring, that's 1/2 kx squared. All right, so it's, when you start out, our initial energy is going to be 1/2 kx squared. So look, we have a block on a spring. It starts out here. We pull it a distance of 20 centimeters and release it. So its initial energy is 1/2 kx squared, right? Plus 0 because it's not moving. When we want to know in the final what it's doing, so that's going to be 1/2 kx squared, and in this case k is going to be your maximum amplitude to start out with, plus 1/2 mv squared, because at some later time it's going to be either here or here, away from equilibrium, right? Because we know we want it to be going 1 meter per second. So it's either gone past or it's gone back. All right? So we just want to figure out the positions, and we know there should be two positions where it has the same speed because we don't care about the direction of the velocity. So we set this up. It turns out we can get rid of all the 1/2s, and we're solving for x. So x squared is going to be equal to ka squared minus mv squared divided by k, and we can say x is equal to the square root of a squared minus m over k v squared. We plug in our numbers, and this is why we needed k. So that means our amplitude, oh boy, well, we lost it, but our amplitude, once we plug in our numbers, our amplitude was, let's see, the amplitude was 20 centimeters. We know it's going to be less than that because that's our maximum, so we end up with something that's 15.4 centimeters. And it's plus or minus because it can be on either the stretched or compressed side. Okay, so let's try this out, pause, and think about this one. Okay, and it turns out this is not going to change. Now, why doesn't this change? Well, does the amplitude affect the frequency or period? No. Okay, what affects the frequency or period? Well, the only things that affect the frequency or period, oh my gosh, why does it keep doing this? The only things that affect the frequency or period, right, omega is equal to k over m. So the only things that can affect your frequency and therefore your period or your other frequency, are the spring constant and the mass. So period and frequency do not depend on amplitude, and you can see there's no A's anywhere in here. All right. Similar to your spring, you have the pendulum. The only real difference with the pendulum is the restoring force, instead of being a spring, is just gravity. And we have to sort of think about this small angle approximation. Here's our restoring force, okay? It's mostly just because we have this component, right? We have some force due to gravity that points down, but because this is a radial and tangential situation, you can break it into components that are radial and tangential, and this becomes your restoring force, okay? So when you plug this in, it gives you the same sort of differential equation, but now your omega depends on different things. So for the spring, it depended on the mass attached to the spring and the spring constant. For the pendulum, it depends on G and the length of your string. Okay, so this is the length of your string. What's G though? G is just gravity. So on Earth, this is always the same. So the length of a pendulum is really what determines its frequency. So if you want a particular frequency, if say you're building a swing, if you want a different frequency, you're going to have to change the length of the attachment of your swing to like your tree or your swing set or whatever. The only other way to change that is to take your swing to the moon or some other planet. Okay, so remember, frequency is once again independent of amplitude. Oops, I guess we did this. Okay, we're going through this again. So if we want to know the pendulum on a grandfather clock, let's say we go tick-tock, that takes about 2 seconds. All right, you plug this in, solve for L. Turns out it's about 1 meter. And if you've seen one of these clocks, they are about 1 meter. You can also calculate the period of this pendulum in the Pantheon in Paris if you put it on the moon, okay? And that's just changing your G values from 9.8 to 1.6. All right, so let's say one person swings on a swing and finds at the period of 3 seconds. A second person of equal mass joins them. Is this going to change the period of the swing? Turns out no, because does the period of a swing depend on mass? No. Okay, if it were a spring, that would be a different story. But because it's a swing, it only depends on the way the swing is constructed and whether it's on Earth or not. So this brings us to damped oscillations. We're not going to worry too much about this, but here's some math that you might want to know about later. This means as this thing oscillates, the frequency and amplitude gets smaller. Forced oscillations, however, are a little bit more interesting. So look, everything has a natural frequency. That means bridges, if you've ever used a wine glass and sort of run your finger around the top to make that humming noise, that thing has a natural frequency. And so here's your response curve. As you change the frequency, right, from a low to a high frequency, at some point you'll get this little peak in amplitude. And the resonance frequency occurs when your external force equals your sort of natural frequency. So the frequency of your driven oscillation equals your natural frequency. And the amplitude is going to depend primarily on, you can get bigger peaks depending on what the amplitude is going to be. And so this has a couple of interesting applications, but anyone that's ever tried to swing on a swing or push someone on a swing knows if you just push them at a random frequency, does anything happen? Well, if you just sort of push someone, you push them every 1 second, if that's not the period of the swing, you're just going to annoy them, okay? But if you push them at the right time, right, when they're at their peak, and that's going to already be their natural frequency, if you use the same frequency as the swing has, then you can get them higher and higher. And if you're the person propelling yourself, you're changing your center of gravity to move yourself higher and higher. So that's finding the resonance frequency of a spring. And remember, we know all materials have resonance frequencies, so you could hypothetically match these up.
This myth needs vocal power, but forget opera singers. Adam and Jamie have gone for full power. The power of rock singer Jamie Vendera.
So Jamie, Have you heard the story that it's possible to break a wine glass with the human voice?
Actually, I have. One of my vocal teachers, a man named Jim Gillette from a band called Nitro, has done it for years back in the 80s, so I know it can be done.
Is a first on television.
A Mythbusters exclusive. 556 hertz, 105 decibels, and 20 attempts makes for a world first. History's been made, and it's been captured on high speed, so there's really no need to try this one at home.
That's nice, huh?